I'm Ymir Vigfusson. I'm at Reykjavik University, and I'm going to be presenting work called Harmonium, which is effectively created by two of my students. One of who is sitting here in the audience, Helgi. And this is also joint work with Microsoft Research, Mahesh, Balakrishnan there. So let's talk a little bit about elasticity. Can you hear me? Maybe I'll just take this with me here. Is this better? So let's talk about elasticity. So we're all aware that elasticity is this notion that when there's a lot of demand for some resources, then we can ramp up the resources that are required to accommodate this spike in load. But just as importantly, we can also dial down resources when we no longer need them. So if we just home in on a single node in the cloud, let's say take a particular host, then really what's going on is that there's some hardware that's being shared, and there's some resources that are being shared between virtual machines. So the canonical ones are, for instance, RAM, CPU, and storage. And there's some hypervisor whose job it is to manage these resources. So let's say that there are 3 VMs living on this machine, then the hypervisor may choose to divide out the RAM across the different VMs, it allocates some number of cores to different VMs, and then finally the storage space on the machine itself is being divided across the VMs. And let's say that there's a surge in load now on this purple VM. Well, what happens? Well, if it is a certain load that requires us to allocate more RAM, then that's something that we can accommodate. We have this nice ballooning techniques. We can even just turn off the VM and turn it back on again with different properties. But we're able to take some of the RAM away from those that don't really need it, some other virtual machine, and put it into this purple VM that now requires it. So we're able to deal with elastically with demand with respect to inner memory. Now, if you look at CPU, well, we can just kind of change the scheduling priority of the purple VM when it requires more scheduling resources and take it away from some other machine. So the red VM may have fewer cycles now, less CPU power to spare, and the purple VM has more. So we're able to deal with elastically with demands in terms of CPU. But what about storage? Let's look at storage. So let's say that there's this demand here. The purple VM certainly needs a lot more storage than it currently has. And well, I mean, the way it's being implemented is that there's some backing file. There's some virtual disk inside the purple VM that has like a large address space, and it's being backed up by some file on the host. And that backing file could be like a file or directory. Really just has variable size. It can be appended to, but we can't really take space away. So when this purple VM grows in terms of requirements for its space, we can't just take space away from the red VM, right? In fact, we don't really have much of elasticity when it comes to storage. So why is that? So really the two things going on here. First of all, we cannot reclaim space that has already been allocated to a virtual disk. Like, we really have no visibility into what's happening in this virtual machine. And second, the virtual disk that has been allocated can't really expand beyond the fixed capacity that is visible to the virtual machine itself. So if we think about the principles that are at work here, when we are creating file systems, we're really following a set of rules in our design. And the rules that we're following, the sacred covenants that we have, include the following. We will believe that all data is created equal. Every single file has the same importance, and it is our holy duty to not lose any data. Like, we must guarantee durability at all costs, right? This is the principle by which we're creating file systems. Is this really relevant? Does this stand the test of time? Is this really true today to the utmost degree? Do we really require durability for everything? I don't know, so I was talking about my laptop just earlier, but my laptop kind of looks like this. I don't know if you've seen this comic here. If you look at some of the documents here, you can like drill down like far down and you'll find some like files that I haven't touched in a long time. And there are so many redundant copies of everything. Like, it's just like really a mess. And this redundancy and these changes in how things are being used and this temporary files and so forth really makes you think about what is really going on in modern storage systems, right? This is courtesy of XKCD. So let's look at this a little bit better here. So we did a little study. We took 3 developer laptops and we just looked at what was on there, right? So because it's just 3 developer laptops, the question is it representative of what we found? And this is a study that we're ongoing. But what we saw was that if you just take a snapshot of the file systems and look at what those files really are, we find that there's a pretty large fraction, between 20 and 30% of the system that's being occupied by some form of cache, right? Or by some media that can be retrieved or swap space. This kind of goes counter to the point that file systems are kind of based on, which is that when you're making a file system, you're trusting that the application itself is, that the application developer is using secondary storage only when durability is required. But that doesn't really seem to hold true, at least not on these systems that we looked at. We believe that this is a representative trend. There's a lot of stuff that could either be recomputed, regenerated, or there are a lot of redundant data. There's even a bunch of data that is just ASCII files that could be compressed if needed. So in other words, there's significant ephemeral and redundant data on a computer. So now let's look at these two pieces that I've been presenting so far and look at them in a puzzle. The question is, can we somehow do something about this lack of elasticity with respect to storage on virtual machines and this durability information that we have here about how data can be recomputed and so forth? The question really is, can we exploit this ephemeral and redundant data to enable elastic storage? Something I want to point out is that this is particularly compounded now that we have flash everywhere, since flash is kind of used both to extend RAM and also used as a cache for your disk. So there's a lot of things that are happening that kind of change some of these covenants that we've been adhering to with respect to storage. So this is the question. Can we exploit this ephemeral data to enable elastic storage? In order to be able to make any progress on this question, we need to come up with some idea. And the idea that we came up with was the following API, like the following kind of interface. So what if every single file on a file system could contract or expand? If we could just think about what that would give us. So if we think about that, we took this forward and we created kind of an abstraction out of it that we call the motif abstraction. So motif is really just a code fragment that is used to generate the data in a file. So that means that a file on your file system, or the Harmonium file system I'll be presenting shortly, implements the two following API routines. It has an expand routine that really creates the raw bytes of the file. And this could be generated by running a computation. It could be decompress the file itself. It could be finishing a MapReduce or even a Spark computation, going back to Michael Franklin's talk. It could be fetching data across the network using SCP. It could be operating over various other files of the file system. It could be a plethora of different things. And then we have the opposite API call, which is contract, which deletes the raw data, the raw bytes that are in the file, retaining only this motif code so that the data can be recomputed when needed. Now, motifs have a number of interesting properties. One of them is that they're recursive, so that you can have a motif that has been contracted, and it depends on a different motif that's also been contracted. So when you expand one, you actually have to expand the other and so forth. And we can, this is something that happens seamlessly in our system. And it's not just this kind of directed tree. It's actually has cycles as well. You can have circular dependencies in the sense that, for instance, a compressed file can depend on the uncompressed motif, and the uncompressed motif can depend on the compressed one, and so forth. So all of this happens kind of seamlessly behind the scenes in the system I'll talk to you about in just a moment. And finally, every single file could actually have multiple motifs. So for instance, if you think about your Git folder, right? In your Git folder, you could simply delete the file that's in your Git because you could get it from an upstream Git repository. Or you could compress it. Or if it's a binary file, you could recompile it using the different source files that are already at your disposal. Or it could be moved on to some network storage. So you could have 4 different motifs, in this case, pertaining to a single file in a Git folder. Okay, so let me just show you how we implement this motif. So this is actual Python code from our implementation. This is a motif that simply moves things to network storage. So when a file needs to be expanded, so there's like an open call that happens, it's all transparent to the user. Open call happens and you need to get the actual contents of the file. Then we call this expand routine, which really just calls SCP and brings the file back onto the system. And when we need to contract it, we simply move it on to the storage server itself. Very simple. That's fully functioning code. Okay. So taking this abstraction a little bit further, we implemented a full-fledged file system out of this. So the idea here is that you have your hypervisor, and you have your virtual machines. Could have multiple one of them. And you have a virtual disk that has some large address space here. And on top of that, you're running the Harmonium file system. The Harmonium file system is trying to retain a particular size limit on the underlying file system itself. So let's say that there's a limit of keeping only 20 gigabytes of data. Then what the Harmonium file system is going to try to do is that it keeps some expanded versions of the files, and it may keep some files in a contracted form. And let's say that there's some application here that requires one of the files that has been contracted. Then what happens transparently and seamlessly is that this file is going to get expanded, and what Harmonium is also tasked with is to make sure that it keeps this limit. So in this case, when it expanded the red file, it may choose a different file and contract that one, so that we maintain the same limit. Okay. So what we can then do, this is what's happening within each VM, is that we have this coordinator process that's living in domain 0 called the conductor. The conductor is responsible for talking to these different Harmonium file systems and telling them really how big this should be. So for instance, the conductor could say, hey, you there, you're supposed to be 10 gigabytes right now, like you're talking to the file system itself. So instead of being 20 gigabytes, this purple VM now has 10 gigabytes of storage to spare, and it needs to contract some of the files. All of this is invisible to the user. It simply means that there's more access latency now when the files are being opened. So what does this give us? This actually gives us an architecture that allows you to scale the different VMs, and thus gives you elasticity with respect to storage on this host. So some questions that pop up when you look at this architecture could be, well, how do you actually choose what files should be contracted? How do you choose what files to expand? And finally, how does this conductor actually talk to the Harmonium file systems? So we'll look at these questions now. So if you look at this question of what should be contracted, we're kind of in a situation where we're given this task, like, hey, you need to free up 5 gigabytes of space. This is something that arrives from the conductor. And there are some files that are expanded, some that are contracted. And we're trying to inject some intelligence into how to make a good choice about what to expand and what to contract. So let's say that, suppose we knew when the files would be accessed next. It's kind of like the same idea that a caching system needs to be able to answer. Then maybe that would be a very useful thing to look at with respect to our optimization, so that we're not taking a file that is immediately going to get expanded. And likewise, something that differentiates us from being a caching system is to try to assess how long it would actually take to expand the file once it has been contracted. So when it's been, when it needs to be expanded again, the open call is going to take X many seconds or something. So if we combine these two things, we actually end up with an optimization question that is in a kind of a brain for the Harmonium file system, which is very similar to a knapsack problem. Really what's going on is that we're trying to choose what files to contract, and we choose them so that we minimize the total expansion latency so that we are saving enough space by doing the contraction. It's a 0-1 knapsack problem here. We looked at a number of different algorithms, and we found that the most competitive one was to look at the whole set of files as kind of an LRU list, and we tried to maximize the ratio of the space savings that you're getting by contracting a file to the expansion latency that would be cost when you need to expand the file itself. Okay, and the second question, which is about the interface here, how does the conductor really talk to the different file systems? Well, what we're needing to communicate is we need to tell the Harmonium file system, hey, you need to shrink by this amount. And then finally, the Harmonium file system needs to be able to say, hey, I've shrunk by 10 gigabytes. You can free up some of the space in the backing file on the underlying file system. So the way it works is that we just have a UNIX socket that we use for the conductor that talks to the Harmonium file system, tells it, gives it directions about how big it should be. And when the Harmonium file system has actually alleviated this space and is ready to have the file shrunk, it uses what is now in many cloud systems, which is that the guest OS can issue trim commands to the virtual disk that gets reflected by the hypervisor. So we evaluated the system. We have a fully working prototype. It's a user space fuse prototype that is written in Python and uses a UNIX socket. And what we did, we wanted to try some trying workloads. So we took 54,000 patch files that are being applied in chronological order to the Linux kernel in order to compile it. And we just try to see how our system would do. And the motif that we're trying here is one that just does network storage. It's the motif I showed you just earlier. And what we're measuring in our evaluation is how long is it going to take to access the first byte of the file. So when you do your open call, when you actually start getting your data. And we're going to be looking also at the size of the file system, because that's what the Harmonium file system is being tasked with, is to try to maintain a particular size. So what I'm showing here is two graphs here. The top one is showing you the latency in milliseconds, how long it's going to take to actually open up the files. And then the lower one is showing you how big the actual file system is. Right now it's at 500 megabytes or so. And the trace here is just, there's just time here on the x-axis in terms of percentages. So what we'll see is that initially, when there are no constraints on the actual size of the file system, there's a really low latency of the open calls. Like nothing really happens. And we can see that the file system is growing. Then all of a sudden, we impose this rule that you can only use 450 megabytes of data. And so what the Harmonium file system is going to do is that it's going to try to contract all the different files that are now open. So now the latencies are going to go up. They're going to spike up to here about 10 milliseconds. But the file system itself is going to gradually now decrease in size until it reaches the limit. And when it reaches the limit, it manages that limit so that when files are being opened and being closed, there's a lot of contraction that's happening in the background. And we can see that's reflected here in these time to first byte latencies. And we put a different limit here at 50% of the trace to use 650. So we're effectively allowing the file system to expand again. And what we can see is that the time to first byte latencies are now shrinking. They're now gradually going down to what they were before, and the file system is expanding back to this limit 650. And when we finally lift the size constraint here, you will see that the file system is just growing gradually as you add more things to it, and that the latencies are back to what they were initially. So they're low latencies. So just to conclude here, what I've been talking about is this problem that we really are lacking some sort of storage elasticity for virtual machines. But what we found was that we have a lot of applications that are effectively trying to store ephemeral and redundant data on secondary storage. And the file systems themselves are heroically struggling to try to fulfill the durability of these files, even though maybe they don't really need to. So what we came up with was this Harmonium file system, where we associate this motif with every single file. This motif tells a file how it could be reconstructed if it were to be contracted. And so we're able to contract and expand in an intelligent fashion so that we minimize the access latency of a file. And what we found is that we have an algorithm based on LRU and some greedy maximization that is able to do a good job at trying to maximize how much space we're contracting given the overhead that we're taking on with respect to latency. We have a fully functioning fuse prototype that I showed you an evaluation on, and what this gives me is this kind of takeaway message for you, which is that I think we're at a point now where we can have elastic performance capacity trade-off for storage in VMs. And with that, I think I'll take questions. Thank you for your patience.
Thank you. It was a very good talk. Questions? Fred?
Hi, Fred Douglas, EMC. So I'm wondering if you looked at things beyond LRU to see if you can do things to try to avoid mistakes where you pick something which looks like it's a good choice because of your particular space efficiency trade-off, but it turns out that you end up deflating something and right after that inflating again and deflating something else which you're about to need right after that and so on. Looking at correlations between data to try to figure out if there are things that you should pick differently.
Yeah, that's a very good question. So effectively what we do is so the question, just to repeat for the camera, is if we looked at anything other than LRU, you could have something like Lattice anomaly or something where you pick the wrong files to expand and contract so that you end up with having a lot of thrashing going on. We looked at a number of different algorithms. For instance, looked at just doing knapsack over the whole thing, where we just tried to look at the estimated time until something is going to be open given time versus the actual expansion, like measured expansion latency latency that would happen. And we found that this gave us slightly better results, but it was really slow. And we really couldn't think of good ways to optimize it. So this greedy approach seemed to do really well. And now that we're implementing this in a faster environment, we're implementing this in C in the kernel and trying to see what happens in kind of real-life scenarios, like given the real type of data that you're talking about. We will probably have to revisit this question and look at some of the other caching algorithms that people have been doing that factor in a lot of these different questions about what happens if you have more or less confidence in whether or not a piece of data is going to be accessed in the future. So that's a very good point. Thank you.
My first question is related to the space. Do you have a, how do you figure out how much space savings you're going to get?
That's a good question. So we have kind of like a little piece of within the daemon itself. We try it. We simply just we try to expand it. We try to contract, and we learn that this particular file has this much expansion, and then we can estimate from that. And we're working on a more intelligent sampler for similar file types. Okay.
So those results don't show the cost of doing that, because that seems like it could be significant.
Yeah, so in this particular evaluation, what happened was that at the beginning, or the first time we actually see a file, we do this kind of test. We try to see how long would it actually take to do the SCP, or how long would it take to compress. And we use those numbers to do the evaluation.
Mm-hmm. And if I could take one more question. Have
Yes.
you thought about what if users may have introduced bugs in your motifs?
Intricate policy about motifs?
Introduce bugs in your motifs.
Oh, that's a good question. Let's see. That is this one here. So, I mean, if you think about that, there's a big security gap here, which is that if you have like a motif that could just do random things, it could destroy your data, it could even be malicious and try to escalate privileges. So what we're trying to do is that we're trying to create like a sandbox on these different motifs so that we can run them so that nothing really bad happens when that motif breaks. We're just going to need to have like an administrator help us out. And with respect to the security itself, we're going to have it so that users need to specifically approve running motifs created by users that have less privilege than themselves. So to like require kind of an authorization.
I'm actually thinking about just bugs as opposed to security vulnerabilities.
Oh, okay.
You just end up destroying your own data because you wrote a bad code.
Yeah. Well, I mean, what would you like to do about it? This happens in reality. But it's a good question. Thank you. Yes.
Dan Williams, IBM.
Uh-huh.
I wanted to ask about, so it seems like not all types of data are going to need an expand, right? Because
That's right.
Especially if they're all, if there's a lot of ephemeral data. How does the system know whether or not any expansion is going to be versus data loss and where you don't care?
Right, exactly. So we kind of push the decision a little bit to the user, so that you create the motifs for the different files that you have. And what we're able to support is kind of like, given this file type, here's a general kind of recipe for that type of file, how expansion and contraction should take place. So if you have a very particular type of ephemeral data, or a very particular type of cache, you can write motifs that correspond to that type of behavior that you want. You could just drop the data, for instance. That could be a policy that you would impose. Thank you. Mm-hmm.
Hi, this is Ritesh here from VMware, and one question was, any thoughts about how to make it transparent for the virtual machine? Because almost this is still a virtual, it's within a virtual machine, the file system. But any thoughts about in a hypervisor context, how to make it transparent to the virtual machine such that it's in the background and the actual VM doesn't change?
I see. So instead of having the file system live inside there, we haven't really given much thought to that question. It involves a lot of changes then to the hypervisor itself, but it's something that would be worthwhile looking into. We just thought this was the simplest and probably the most straightforward layer to do the implementation work, but there's no real reason why this transparent layer needs to live there in the stack. That's a good point. Yes?
Peter Desnoyers, Northeastern University, and this is very interesting. Following up on that question, it does seem there's two aspects here. There's the mechanism of being able to get away from your rigid volume size on a file system, and then there's your policies of how to handle what to do with the storage.
Right.
And so have you thought about if it were, in many environments that would typically be done, in a uniform way on the other side of the hypervisor boundary, and also, it's possible that an object storage mechanism, for instance, would make a similar interface that avoids these volume, limits.
Yeah, that's an interesting question. I mean, there's nothing really special about the way we architected the hypervisor, the way we interface with the hypervisor, because we just created our own Harmonium process that's living in domain 0. That could be a part of the hypervisor. It could be it could be pretty much anywhere. With respect to your question, we haven't really thought about this type of generalization for the problem of like looking in object store, but certainly it's an example of this kind of trade-off that's going on. Like we have this trade-off now between like storage, network, and computation that's going on, and we're really exploring one part of that trade-off, which is that what if if storage is expensive, can we use the network, or can we use computation to kind of alleviate some of the burden that's being placed on that? And this is an example of that, and I think that applies also in object store settings as well.
Thank you.
Thank you very much.
Okay, let's thank the speaker again.